A linear transformation is called an isomorphism if we could show that it's a one-to-one and onto linear transformation. Here, we have these two matrices here, and we are going to see if this matrices under the linear transformation defined by a matrix is an isomorphism. So we could need to show that it should be both one-to-one and onto. For one-to-one, we need to show that the kernel of T contains only the zero vector. Okay? Only the zero vector of the identified linear transformation. And since we have here 2 by 2 matrices, so the kernel of T should be equal to the zero vector of our R2. Our R2. Aside from that, we also need to show the relationship of onto linear transformation. The onto linear transformation can only be determined if the dimension of your range or the dimension of the basis of the range is equal to the dimension of your domain. Okay, so these are the two considerations specifically for one-to-one and onto respectively, so that we could show that this the linear transformation defined by these two matrices is an isomorphism. So using the first matrix, let's show first if this is a one-to-one linear transformation by showing whether the kernel is equal to the zero vector. Take note that if we're going to solve for the kernel, it's same thing as this. So by showing that the linear transformation by multiplying matrix A by a certain vector is equal to the zero vector here. Again, we have here R2 to R2. Since this matrix is a 2 by 2 matrix, being m by n, the linear transformation here is defined as r to the n to r to the m. In short, our linear transformation here is r2 to r2. In short, the zero vector here is again the zero vector in r2. That's 0, it should be 0, 0. And the vector that we're going to use here is also an element of R2. So we're going to show it like this. The first step in solving for the kernel is actually coming up with the reduced row echelon form of this matrix, negative 1, 0, 0, and 1. Let's try to come up with its reduced row echelon form. So we're going to multiply negative 1 to row 1 for a new row 1. We have here 1, 0, 0, and 1. Once we reach this reduced row echelon form, let's multiply our vector v sub 1, v sub 2, and equate to the zero vector. Sorry, that's just 0. 0, 0. This means that v sub 1 is 0 and v sub 2 is 0. Okay? With this, the vector that will satisfy this equality here is the zero vector in R2. With this, our kernel now is a set containing 0, 0. And with this identification, we have shown that this first matrix here is a one-to-one linear transformation because its kernel is the zero vector. Okay? So this is already a one-to-one linear transformation. Now, how do we show that it's onto? Let's look at our what do you call this one? Our linear transformation described here. You have here R2 to the R2. In short, the dimension of your domain, this is your domain, okay? The dimension, let me write it here. The dimension of your domain is equal to 2, as this is the space here, R2. Now, to show that this is an onto linear transformation, we need to show that the dimension of the range is equal to the dimension of the domain. How do we show the basis, or the basis for the range? The basis of the range will be identified by the number of columns that are part of the column space of A. Column space of A here. So we're going to look at this final form, this one here, the reduced row echelon form, 1, 0, 0, and 1. We can see here two columns containing leading 1. Okay? So the basis for the range here is the set containing the column space or the columns of our initial matrix. So you will have your negative 1, 0, and then 0 and 1. Okay? In short, the dimension of the range, which is also equal to the rank of T, is equal to 2, since there are two vectors that are part of the basis of the range. Since the dimension here of your domain, which is 2, is equal to the dimension of your range. 2 equals 2. This means that our linear transformation here is an on 2. And with this 2 here, okay, our linear transformation using the first matrix is an isomorphism. Though this is not the label or the headline of this, what do you call it? This one, the label, or for this video, one-to-one onto linear transformations, you just need to insert this idea. This is one-to-one linear transformation because your kernel contains 0 vector itself, and it's onto because the dimension of domain is equal to the dimension of your range. So the first matrix under linear transformation is in isomorphism. Now, I hope that the space here would be enough for me to show the relationship of the next matrix here. So same thing, we need to show whether this is onto and one-to-one. For one-to-one, we need to show that the kernel, okay, is equal to the 0 vector. So same thing, transformation of V is equal to this, must be equal to that. And since it's also a 2 by 2 matrix, we're also going to use this one here. And let's come up with the reduced row echelon form of this matrix. You have 1, 0, 0, negative 1. So you multiply negative 1 to row 2. So you will have this reduced row echelon form, which will be used for both the identification of one-to-one and on-to. Once we multiply our vector here and equate to our 0 vector in R2, V sub 1 is also 0, V sub 2 is 0. Hence, the vector that satisfies this is the 0 vector in R2. This would mean the kernel of T for this matrix is a set containing the 0 vector. And with that, we can say that this is a one-to-one linear transformation. Okay? One-to-one linear transformation this time. Now for onto, we need to look at this reduced row echelon form. And since again, this follows the same transformation here, the domain, or I mean the dimension of your domain is already equal to 2. What we need to show here is whether the dimension of the range is also 2 using the reduced row echelon form already identified earlier, 1, 0, 0, 1. We have 2 columns containing leading ones. In short, our basis for the range of T in this case is a set containing the 2 columns of our initial matrix. You will have here 1, 0 and 0, negative 1. With this, we can say that the dimension of your range of T, since there are 2 elements there, is also 2. With this idea that the dimension of your domain is equal to the dimension of your range, which is 2 equals to 2, this is also an onto linear transformation. And with that, one-to-one here, onto here, this is also an isomorphism. Okay? So this is how we determine one-to-one and onto linear transformations. We only need to, again, come up with the reduced row echelon form. And of course, more importantly, declare the type of linear transformation. And with that, we also inserted the idea of isomorphism once we have shown that the linear transformation is both one-to-one and onto. Thank you very much for watching.